So this is part 5 of chapter 9. Last video in chapter 9. Yay! So we went through a lot in chapter 9, but the part 4, which is the part that's connected, well, it's all connected, of course it's all connected, but the part most closely connected to this, so parts 4 and parts 5 of these videos are trying to explain the type of bonds that are happening to make these shapes that we talked about at the beginning of the chapter, because we know these shapes really happen. But the behind the scenes, how do these shapes happen based on the electrons? That's what we're looking at. So there's two different approaches, two different explanations on how the VSEPR theory works. Neither one is right or wrong. They both work. So since they can't, no scientist has been able to prove that one is absolutely 100% better than the other. So we have to learn both theories, both approaches, because one could be right, the other one could be right. We don't know. So they're both equally likely to be correct. So the hybridization is the beginning of the first of those theories. Hybridization was us saying SP or SP2 or SP3 or SP3D or SP3D2. We determined the hybridization by looking at our Lewis structure, counting the number of electron domains, and then that is the number of orbitals that the central atom will hybridize. So if it has 3 electron domains, it needs to make 3 brand new orbitals ready for bonding, ready to be this. If it's a central atom, then it's like the leader. It has to be in charge. It's got to make some sacrifices. So that's it making its sacrifices. So the beginning of this video is going to be connected to that. It's like, so we've made our hybridization. We've made our new hybrid orbitals. Awesome. But in the last video, we didn't talk about when they overlap with other orbitals, what that was. So that's what we have left. So we've hybridized our central atom. Their new sp2 orbitals are ready to go. They're ready to bond. So what can those hybrid orbitals now do? Okay. So valence bond theory is once the central atom is hybridized, how are those hybrid orbitals going to overlap with their outside atoms? Okay. There are 2 different ways these hybrid orbitals can overlap to the outside atoms. Okay, the first one is a sigma bond. A sigma bond, they define it as a head-to-head overlap. So bonds don't actually happen in straight lines. Like we draw this little happy straight line when we draw our Lewis structures that represents a bond, but that's not really what happens. It's these gushy clouds full of electrons overlapping, okay? But if they overlapped like where you drew the line, like when you're drawing your Lewis structures, that would be a sigma bond. Okay, it's just the 2 orbitals just overlap kind of like a straight line. There's cylindrical symmetry. That means if you rotate it, it looks the same on all sides. So sigma bonds, head-to-head overlap, and there's cylindrical symmetry. Okay. The second type of bond are pi bonds. So in this picture, this is where the sigma bond would be right there. The pi bond is happening here and here. Now it looks like there's 2 pi bonds, but there's only 1 pi bond. These pi bonds always happen between p orbitals. And remember, this is 1 p orbital. This is the second p orbital. So this is only 2 p orbitals overlapping. So it's only 1 pi bond. So we call this side-to-side overlap because it's overlapping not where the line would be when I drew the bond, but above it and below it. So the electron density is above and below the internuclear axis. The internuclear axis, where the sigma bond is happening. Okay, pi bonds only happen between p orbitals. So they're actually not going to happen between the hybrid orbital and the outside atom. It's going to happen between one of the leftover p orbitals. So if something is sp2, 1 s orbital and 2 p orbitals smushed together to make these magical brand new hybrid sp2 orbitals. But wasn't there 1 p orbital that was left behind that was not being used? Well, that buddy could do a pi bond then. Just a straight up p orbital. Okay. So, single bonds. Single bonds are sigma bonds. Okay, so every single bond that you draw in a Lewis structure is a sigma bond. Okay, double bonds. The first bond is a sigma bond. The first bond between any 2 atoms is always a sigma bond. But in a double bond, it bonds twice. So once is going to be the sigma bond. The second bond has to be a pi bond. And the reason why it has to be the pi bond, we cannot have two sigma bonds at the same time because there's not enough space. Once you've made the sigma bond, there's no space to do a second bond there. That location is taken. So it's like two people trying to sit down in one chair. Once one person is in one chair, that space is taken. Someone's got to find somewhere else to go. Okay, so they can do a pi bond. So above and below where the other person is. Okay, so a double bond is made up of two bonds, one sigma bond and one pi bond. So a triple bond, one sigma bond and two pi bonds. Okay, so this is just trying to show us a picture. So in this scenario, carbon has 3 electron domains. 1, 2, 3. So it is sp2 hybridized. So that's what this and this and this are, the 3 sp2. So there are 3 sigma bonds happening. Let's change colors here. This is a sigma bond, so the purple ones are sigma bonds. Sigma bond, and then one of these will be a sigma bond. So there it is. 1, 2, 3. Well, the double bond, that's going to be 1 sigma and 1 pi. So this is the pi bond happening between this p orbital that's not part of the sp2. It's the leftover p orbital is what's doing that. Okay. So again, I know it looks kind of like there's 3 bonds, like 1, 2, 3. Well, what you've got to remember is that this pink stuff above and below, that's all the same orbital. That's 1 p orbital on the carbon sharing with 1 p orbital on the oxygen. So that's just 1 bond. Okay. So kind of what's happening is the sigma bond is on the x-axis and the pi bond is on the y-axis. Again, we cannot have things taking up too much space. Okay, we can't have 2 things on the x-axis. We have 1 thing on the x-axis, so we have to go to the y-axis. And then if we had a triple bond, we would have the third bond, or the second pi bond would be along the z-axis. That's why we cannot have a quadruple bond, because we live in a 3-dimensional world, so there's only 3 dimensions, so there can only be 3 bonds. Otherwise, we run out of space. Okay. So this is trying to show the triple bond. They didn't do the fuzzy cloud, so like how this one, they did the fuzzy cloud. They didn't do that over here because otherwise you couldn't see anything. So here's the sigma bond. Change colors. Yeah. Here is 1 pi bond along the y-axis, and here is the other pi bond along the z-axis. Okay, so just to clarify, sigma bonds. Their head-to-head overlap. They're on the internuclear axis, where your line was, and all single bonds are sigma bonds, and all first bonds between 2 atoms are sigma bonds. Color thingy, where are you, color thingy? Nothing? Okay, so apparently everything's going to be red. Pi bonds. Oops. Symbol first. Pi bonds. They are side to side overlap. Above and below the internuclear axis. So I'm going to write y-axis here, or sorry, x-axis. These are y and z-axis here. And they are second bond in a double bond, and the second and third bond in a triple bond. So be prepared to answer these types of questions about sigma and pi bonds. I could just draw you a structure and say count how many sigma bonds and count how many pi bonds there are in this structure. Oops. So actually, if we're we'll practice here in a minute with that. Okay, so now we're gonna there we go. Look at how this is impacted by resonance. So we're going to take these sigma and pi bonds and look at it for resonance. Okay, so resonance it was when we drew a Lewis structure and we had at least one double bond, and that double bond is actually shared between multiple other bonds, where that double bond could have been moved. So in this is nitrate polyatomic ion. All three of the Lewis structures that are shown here are correct. In terms of they all follow the Lewis structure rules. In real life, we don't see a double bond in one spot and a single bond in another spot and a single bond in another. What we see is 1 1/3 bonds in all three spots. So what happens is that double bond is actually shared. So real life is like a combination of all this. And the way we know that that happens is instead of seeing this, which would be a sigma bond, sigma bond, sigma bond, pi bond. Okay, double bond here, single bond, we don't see that. We see this instead. So we're seeing that pi bond being shared. So the resonance structure actually looks like this, where the double bond is shared between all three of the bonds. Okay, so that's why we said in chapter 8 that things that have resonance, we can count their delocalized electrons. Those are the electrons being shared among multiple bonds. Okay, they're being shared throughout the entire molecule or the entire ion. Okay, so with this one, this was one of the examples that we used in chapter 8. It had 6 delocalized electrons, because if we look at this structure and this structure, those double bonds moved, but both structures are correct. So in real life, what we see, instead of seeing double, single, double, single, double, single, we see this. So it's not something to worry about right now, but for those of you going on in chemistry and you're going to get to organic chemistry, this molecule, that's horrible, I'm sorry, doesn't look like that by most organic chemists. It typically looks like this because of that O. So again, single bonds. It's 1 sigma bond. Double bonds. It's 1 sigma and 1 pi. Triple bonds is 1 sigma and 2 pi's. Talking to my students. They're going to listen. They're going to watch the video later. Okay. So I made that way bigger than I wanted to. I'm going to draw a molecule, and we're going to count how many sigma and pi bonds are in this molecule. And it's going to be a big molecule, not one you would be expected to draw. Okay. So we're going to look at this molecule, and we're going to count the number of sigma bonds and the number of pi bonds. So we need to look for every single bond and every first bond between atoms. So first we'll do single bonds. So I'm just circling them right now. We'll come back and count them in a second. Okay, so now I'm going to look at my double and my triple bonds, and I'm going to circle one of the lines, leaving the other one open. So sigma bonds, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pi bonds. Oh. 1, 2, 3, 4. So we have 10 sigma bonds and 4 pi bonds. So that ended our first explanation on how the shapes happen. So hybridization and valence bond theory together are one explanation. The second explanation is the molecular orbital theory. We're going to stay relatively simple with this. Molecular orbital theory gets complicated real quick. So we're only going to look at diatomic molecules, so 2 atoms in a molecule, okay? But the idea of the molecular orbital theory is that it's not just the central atom. So in hybridization, the central atom changes. It hybridizes its own orbitals, but the outside atoms, they don't change at all. In the molecular orbital theory, every atom in the molecule pretty much undergoes this hybridization, but instead of just with itself, it merges all the orbitals of all the atoms and instead turn around and make brand new orbitals just for the molecule. Okay, so that's what the molecular orbital theory is. All the atoms mush together all their orbitals and then make these brand new molecular orbitals that happen within the molecule. And when we think of these molecular orbitals, kind of like waves, okay? And with waves, if you have one wave and then another wave, and they're going together, that's a constructive. It's constructive. They work together, okay? Or if I have this wave and this wave, that's destructive. When one is up, the other one is down. They're working against each other. So when we're looking at these molecular orbitals, sometimes we have orbitals that work together, and those are called our bonding orbitals. They're the electrons working together, forming bonds. Everyone's happy. Then we have our anti-bonding orbitals, which are our destructive orbitals, where the electrons, that's pretty much showing the repulsions, the electrons moving away from each other, okay? So the wave nature of electrons, that was back in chapter 6 when we looked at waves. We're not going to be calculating wavelength of frequency or anything like that. We're just looking at constructive versus destructive. Okay, so we have bonding and we have anti-bonding molecular orbitals. Anti-bonding molecular orbitals are going to have these asterisks next to them. So like we see one right there. That's how you can recognize it is anti-bonding. And the other way is when we look at this one, this bonding orbital, we can see that that's like a bond. There's the 2 atoms and they're bonding. In the anti-bonding orbital, there's a node. You may or may not remember from chapter 6. A node is a place where electrons cannot be. So there is a node between those 2 electrons, which means that they cannot bond. There is like a wall between them. So the electrons cannot be bonded. So in molecular orbital theory, again, what's going to happen is we're going to show the atomic orbitals of one atom and then the atomic orbital of the other atom. We're only going to do diatomic molecules, which means we can only have 2 atoms. So that's why we can just have one atomic orbital column and a second atomic orbital column, because you guys aren't going to see anything that has more than 2. And then in the center, we're going to have our molecular orbitals. These are the new orbitals that are made by smushing the 2 atomic orbital columns together. Okay, so this is how our molecular orbitals are going to look. Now the good news is I'm going to draw this picture for you. Your job is going to be to fill in the electrons. So what's happening with H2? Well, the atomic orbital, this is for hydrogen. This is for hydrogen, and then the molecule I'm making is H2. So what first I'm going to do is look at the electron configuration for hydrogen. It is 1s1. So there I drew a 1s orbital and put 1 electron in it. Then I look up the electron configuration for hydrogen, the other atomic orbital. Well, it's the same thing, so 1s1. This one, it shows the electron pointing down. I don't know why. It would be pointing up is what it would be doing, okay? So what's going to happen is this orbital and this orbital are going to smush together, just like they did in hybridization, and then they're going to spit out 2 new orbitals. And then those 2 orbitals are drawn in the center, the molecular orbitals. One of them's down here, and one of them is up here. Again, I'm going to be drawing these pictures for you. You're not going to be drawing the pictures. Okay. Oh, well, I want to keep that. So that means that this orbital and this orbital are gone. They were used to make these other 2 orbitals. But the electrons inside of those orbitals have to go somewhere. And there was 1 electron over here and 1 electron over here. So I'm just going to use those electrons to go into the molecular orbitals. I follow the same rules I did for electron configurations. Fill the lower thing before the higher thing. So up, down. The molecular orbital configuration for H2 is sigma 1s2. So the sigmas are representing sigma bonds. The star up here is showing the anti-bonding. And the sigmas for the sigma bonds, the 1s is showing, hey, this was made up of taking two 1s orbitals and smushing them together. So hydrogen's the simplest one to do. But as we go into more orbitals, we're going to see more complicated things. But the last thing that we're going to talk about before we practice some more is the bond order. We've talked about bond order before, I just didn't call it that word. We've seen single bonds, double bonds, and triple bonds. The bond order of a single bond is 1, the bond order of a double bond is 2, and the bond order of a triple bond is 3. In this molecular orbital thing, you can't just like eyeball that and see it. So we've got to have a way of figuring out the bond order. And we've also seen bond orders of like 1.5 and 1 1/3. That was when our resonance happened and the bonds were being shared. So here's the equation to calculate the bond order. It's 1/2. And then we take, the number of bonding electrons minus the number of anti-bonding electrons. I'm going to put an asterisk right there because that's how you're going to represent, or that's how you're going to know that they're anti-bonding orbitals. So when we're doing this, we're just looking at the center thing. So we look at our center thing and we're going to find our bonding orbital, this one, and our anti-bonding orbital, this one. And we're just going to count the number of electrons. So bond order, 1/2 times the number of bonding electrons. Well, there's 2. Number of anti-bonding electrons. Well, there's 0. So 2 minus 0 is 2 times 1/2 is 1. That's telling me hydrogen is going to be single bonded to the other hydrogen. Okay. So there it is. Go us. Okay. He2. This would be trying to take 2 helium atoms and make it into a diatomic helium molecule. So again, we've got on the left what the electron configuration for helium is, and we draw the orbital diagram. So we draw the box with the arrows. All the way on the right, we have the other helium. We draw its orbital diagram. It's 1s2. And then in the center, this and this smushed together to make those central things. Do you see those dotted lines on the outside? That's showing you, hey, by the way, this and this made those. So there were 2 electrons here and 2 electrons here. So into the molecular orbitals, I had to put a total of 4 electrons. So we put 2 on the bottom, 2 on the top. If we do our bond order, it's 1/2 bonding minus anti-bonding. So 1/2, 2 minus 2, 2 minus 2 is 0, times 1/2 is still 0. That means He2 will have 0 bonds between it, which means it doesn't exist. So we can kind of predict if things are going to exist or not. Now, once we get beyond hydrogen and helium, we're going to start seeing p orbitals. We are not looking into the d orbitals. We're not going that far. But with p orbitals, what happens is we have the possibility now for sigma bonds and pi bonds, because pi bonds happen between p orbitals. So this is what the diagram looks like. Again, atomic, I'm just going to say atom 1, atom 2, and then in the middle is the molecule. Okay, so it's not until the 2 p's that we started seeing p's, so that's what happened here. If we look at the center stuff, we've seen this. This looks just like the 1. Up here is the p's. So if we count, we took 1, 2, 3, 4, 5, 6 boxes. So the 3 boxes for 2p and 3 boxes for 2p make 6 boxes. So if you look in the center, there's 1, 2, 3, 4, 5, 6. Same number of boxes. Okay, so we're going to follow the same rules that we did for electron configurations. You got to fill up the bottom box before you move to the next one. If you have 2 boxes that are degenerate, so are the same energy, you can split the electrons between them. So let's try one. Let's do, race. Let's do N2. So the molecule I want to do is N2. So on the left I'm going to put a nitrogen, and on the right I'm going to put a nitrogen. the molecule will be given to you, and then you're just going to take the two atoms that are in it, put one on the left and one on the right. Okay. All the examples we've done so far, they're the same element, but we'll do some examples here in a minute where they are not. So what you're going to do is let's do the left column first. So N. We're going to look at the electron configuration for N. It's 1s2, 2s2, 2p3. So 2s2, 2p3. 1, 2, 3. Now I'm going to do it for the other nitrogen as well. Well, it's also 1s2, 2s2, 2p3. 1, 2, 3. Okay. So that's how they start. They start as separate atomic orbitals. And then what happens with the molecular orbital theory is all these boxes are going to smush together and make brand new molecular orbitals that we only see for N2. So we've got to figure out where those electrons that used to be in the atomic orbitals went once they moved into the molecular orbitals. So down here, I've got 2 electrons and 2 electrons. So I have 4 electrons. And they're all connected to this, right? Notice there's dotted lines connecting them. So those 4 electrons have to stay within that world. So I'm going to put the 4 electrons in these inner boxes. 1, 2, 3, 4. Up above, I have 1, 2, 3, 4, 5, 6 electrons. So those electrons have to stay within this 2p world. So 1, 2, 3, 4, 5, 6. That's going to be my molecular orbital diagram for N2. So let's calculate the bond order. The number of bonding electrons. So the bonding electrons are in the bonding orbitals. So they're ones that don't have stars around them. Okay, so I'm going to count. There's 2, 3, 4, 5, 6, 7, 8. And then we need to count the number of electrons in the anti-bonding orbitals. So they're the ones with the stars. Star, star, star. There's 2 and then 0. So 8 minus 2 is 6 times 1/2 is 3. So this would be a triple bond, is what that's telling me. So I calculated the bond order. Now, I would not expect you to come up with this picture on your own. What I mean by that is if I erase all the things that I wrote on this. I would give you this and say, all right, do it for N2. And then you would have to fill in the atom over here, fill in the atom over there, and then put in your electrons. And do what we did to put in the electrons. And then I could ask you what the bond order is. Okay, that's what's going to be expected of you for the molecular orbital theory. You're not going to be expected to memorize what these molecular orbitals look like in their order. It's filling in the electrons. Okay. Now there are a couple of elements within the P block that do weird things where their picture like this looks a little bit different. This flip-flops with that. Again, I'm the one giving you the picture, so you don't super have to worry about it. There is a question in Mastering Chemistry, though, that has these exceptions, so just look at the pictures that you're given, okay? So, the weird ones are boron, carbon, and nitrogen, okay? They're the weird ones, okay? Oh, last thing, vocab words.
Mommy, now what you mean?
Yes, you can go get some water.
No, I want to meet you.
You're gonna have to wait. Okay, so paramagnetic and diamagnetic. Paramagnetic is when you have unpaired electrons. Diamagnetic is when all electrons are paired. So unpaired electrons, when there's one arrow in a box. So if there's any arrows alone, it is paramagnetic. Doesn't di means 2? So diamagnetic is when everything's in sets of 2. So I remember that. So paired electrons. So if we look at this, this is just them drawing the molecular orbital diagrams just without all, they didn't do the left-hand column and the right-hand column, they just did the center column. So in B2, don't we have some unpaired electrons? Which is why B2 is paramagnetic. In C2, all my electrons are in sets of 2. So it's diamagnetic. In N2, all my electrons are in sets of 2. So it's diamagnetic. In O2, I have some unpaired electrons, so it's paramagnetic. In fluorine, they're all paired, so it's diamagnetic. And in neon, it would also be diamagnetic. The only reason why there's nothing written there is because it has a bond order of 0, which means it doesn't exist. So, wrapping up the molecular orbital theory. Be prepared to fill in electrons in a molecular orbital diagram that you were provided. So I would give you the molecular orbital diagram. I'd tell you the molecule and say fill in the electrons. Then I could ask you what's the bond order? And then I could ask you, is it paramagnetic or diamagnetic? That's what I want you to be ready for. Okay. So just reiterating, the molecular orbital theory is one way to describe how those shapes happen. So what the molecular orbital theory is saying, that the shapes happen because the molecule makes its own orbitals, and then they can come together in whatever shape they need to, and that shape is linear or trigonal planar or tetrahedral or trigonal bipyramidal or octahedral or bent or whatever it is. So molecular orbital theory is explaining how they can come together in those shapes because they made their own molecular orbitals and they can do what they need. Hybridization in the valence bond theory is another explanation for that, but what it's saying is that the central atom hybridizes, not the whole molecule. Molecular orbital theory is the whole molecule smushes together. In hybridization, the central atom hybridizes. And then we see sigma or pi bonds happening between them. The outside atoms don't change in what their orbitals are. So that's the how does it happen?